In this brief lecture, I will summarize the elaborate lecture on double layer and introduction to electrochemical kinetics. And I will also document the clarifications that were discussed during the discussion session following the lecture. We had introduced Ellingham diagram to stress one single point, which is if we want to break an oxide thermally into its components, you would require very high temperature. There is a lot of information available in this diagram. We won't go into all the details, but we will stress on few points that were discussed during the discussion session. On the y-axis is plotted the free energy of oxidation of elements. For example, if you take this particular line, this quantifies the oxidation of titanium into titanium dioxide at different temperature. You can interpret different oxidation values for oxidation of different metals based on their electronic configuration. For example, titanium is a D2S2 element. So all the elements present in this period, titanium, zirconium, hafnium, would have very negative oxidation energies. For example, this is fairly negative compared to certain other elements. For example, copper has an electronic configuration of D10S1 or D9S2. So when you oxidize copper to form copper oxide, this is a weak oxide compared to titanium dioxide. So there are one information that is conveyed in this diagram is the relative exothermicity of different oxides. In addition, there is melting point and boiling point that are conveyed in this diagram. There are three distinct kinds of lines in this diagram. One are lines which have a slope in this manner, and there are few oxidation reactions which do not have a slope, and there are even fewer reactions which have a slope in this manner. Why is that so? All this depends upon the number of molecules that are present in the gas phase versus the number of molecules present in the gas phase on the product side. I mean, the number of molecules that are present in the gas phase in the reactant side versus the number of molecules that are present in the gas phase in the product side. For example, if you take this reaction on the reactant side, that is titanium and oxygen, oxygen is present in the gas phase and there are no gas phase products. So when you quantify configurational entropy, for which you have to go and reach out to your chemical thermodynamics background, if you quantify the configurational entropy of the reactants is greater than the configurational entropy of the products, because configurational entropy is predominantly determined by molecules in the gas phase. As there are molecules in the gas phase on the reactant side and no molecules in the gas phase on the product side, configurational entropy will always favor the reactant side. So as the temperature increases, because delta G is given by delta H minus T delta S, temperature would favor that side which has greater configuration entropy. So because the reactant has greater configuration entropy, temperature will tend to favor the reactant side. Therefore, the delta G of this oxidation, that is titanium oxidation to titanium dioxide, will decrease. Enthalpy will favor titanium reacting with oxygen to form titanium dioxide, because typically one simple way to think about this is the electrons that are in on titanium. Okay, a qualitative way to understand this: electrons that are present in the titanium orbitals, that is D2S2 orbitals, are being transferred to oxygen, which is more electronegative. Therefore, titanium dioxide is very stable. However, as the entropy for in this reaction, that is titanium getting oxidized to titanium dioxide, entropy decreases. Therefore, with increase in temperature, the exothermicity of the reaction decreases. That is why these oxidation reactions are sloped in this manner. That's also true of most of the oxidation of metals. There are some reactions here, like carbon plus oxygen giving CO2. The line is flat, there's no slope. That is because the number of molecules that are present in the gas phase is the same in the reactant side as well as in the product side. Carbon is a solid, oxygen is in the gas phase, CO2 is also in the gas phase. Therefore, the number of molecules that are present in the reactant side as well as the product side is just the same. So there is no change in configuration entropy when you go from the reactants to the products. Therefore, temperature does not have any, when you calculate delta G is equal to delta H minus T delta S, because delta S is approximately zero, temperature does not really contribute to changes in delta G. Therefore, this line is flat. And there are some other reactions which are sloped in this manner. Why is that? If you look at this reaction, the number of molecules that are present in the product phase, this here, 2 carbon monoxide, that is more than the number of molecules that are present in the gas phase on the reactant side. So we have only oxygen in the gas phase and 2 carbon dioxide molecule in the product phase. Therefore, the configurational entropy of the products is more than the configurational entropy of the reactants. Therefore, as you increase the temperature, delta G will increase even further. Enthalpy itself favors oxidation. In addition to that, entropy also favors oxidation. Therefore, as you increase the temperature, the delta G becomes more and more negative. So this is an important diagram, but in the context of what we are trying to convey is the following. That is, if you want to break the oxides thermally, you would require very high temperature to break the oxides. As opposed to that, if you want to break the oxides via electrochemical means, it can be done at room temperature and pressure. For example, the oxide which is of interest for many electrochemical systems is that of water, is that of oxygen, which is water. While it requires enormous, very high temperatures to break water thermally. Why is that so? Because if you look at this reaction, this is sufficiently exothermic. Okay? Even though the exothermicity decreases with temperature, if you just want to thermally decompose water, it requires very high temperature. But water can be electrochemically dissociated into oxygen and hydrogen gas just at room temperature and pressure. Okay, so it is not that the thermodynamics of water oxidation is changed. Okay, so when you do the breaking of water molecule into oxygen and hydrogen thermally and electrochemically, thermodynamics is not changed. That is, what is endothermic continues to remain endothermic in this case also. I mean, the breaking of water molecules to hydrogen and oxygen at a particular temperature and pressure, if it is exothermic in this diagram, it will continue to remain. I mean, if it is endothermic based on this reaction, it will continue to be endothermic when you are looking at electrochemical conditions. However, the kinetic pathways become more facile. Here also we need energy to be supplied to break water into oxygen and hydrogen. But when you supply that energy electrochemically, the electrochemical potentials go towards modulating the chemical potential of electrons. Okay, so the electrochemical potentials couple directly to the energy of the electrons present in this reaction and in this half reaction, because electrochemical potentials dominantly change the energy of electrons involved in this half reaction, and in this half reaction, the electrochemical breakage of water to oxygen and hydrogen is more facile compared to the thermal decomposition of water, which requires very high temperature. So this is one of the simplest example where the power of electrochemistry can be illustrated. Okay, so the electrochemical conditions are relatively benign compared to the conditions required for thermal decomposition. Okay. So we had also discussed some aspects of electrified interface. Based on the questions, I would like to reinforce certain points. One is that if you look at the solvation around anion and cation, they show different behavior. This is because typically when a cation is formed, the water dipoles present in water are able to bind better when it comes to a cation. So the heat of solvation is more negative when cations are solvated compared to anions. That is, the interaction between water molecules and a cation, a typical cation, is more. These bonds are stronger. These are ion dipole interaction. These ion dipole interactions are stronger when it comes to water molecules interacting with a cation, and these interaction between water molecules and anions are less stronger. Therefore, it is possible to strip out the anion molecules of the waters of solvation, and the anion molecules will tend to directly bind to the electrode surface. As opposed to this, it is harder to strip out water molecules out of this solvation sheath surrounding the cation molecules. So the cations typically interact with the electrode via the water molecules. Okay, so that is the difference that was discussed in the discussion session. So, and there are certain other notions which is also illustrated in the schematic. There is this compact layer, that means the first layer of the anions and cations this distance, that is the distance, this sort of gives the distance between the first row of cations that are binding to this electrode. Okay, so this gives the first row of anions that are binding to the electrode. Okay, so that distance is denoted by this compact layer. Okay, so besides, beyond this layer, the cations are mobile. Okay, so that is, once these cations are fixed, okay, or bound to the electrode, we typically they don't get. We typically think that they don't get detached and move on. Okay, beyond this layer, the notion is that the ions move around. Okay, so you should also understand that these were notions that were envisaged in the early days of electrochemistry, where thermal imaging, I mean, not thermal imaging, imaging was not possible. Imaging at a molecular level was not possible, right? So in reality, you would not have a sharp interface between the electrode and electrolyte. Here, we imagine a sharp electrode. So that is an idealization. So these kinds of models, like there are some molecules which bind directly to the electrode surface. There are some molecules, some ions that bind via water molecules, and there's a compact layer and there's a diffuse layer, is going to be useful when we address capacitance in a more quantitative manner as we progress in this course. Okay, so these distances are going to be useful in coming up with a quantitative value for capacitance that will be present in these kinds of systems. So these issues were discussed in the discussion session. So an important length scale is the Debye length scale, that gives you the magnitude of the electric field that is present. To obtain the Debye length scale, it is enough to know the concentration of ions that are present in the solution. And what we try to emphasize is that the electric field that is present is fairly high. Electric field that is present in electrified interface that you see in an electrochemical double layer is fairly high. The capacitance is not that high, but even I mean, this is a normal capacitor. If you just dip a metal plate onto a reasonably concentrated solution, you will get this kind of capacitors. But it is possible to get much more capacitance in what is called supercapacitors. For that, you actively work towards increasing the double layer surface area. Okay, so here it's a flat surface. So this is not a rough surface. So the amount of surface area which you can get from this interface is very less. In practice, if you want to increase the capacitance, what you would want is that the interface should be very corrugated. It should be very rough. As the roughness increases, the electrochemical surface area available for the formation of this double layer also increases. The greater the electrochemical surface area, there will be more ions that are bound to this electrode, to an electrode. Therefore, the capacitance is also greater. So such a strategy is utilized for, in the case of, let's say, carbon electrode. You can form very highly porous structures from carbon typically. These are called aerogels and so on. And also even for metals, you can have porous structures, foams. Okay, for example, nickel foams will have very high electrochemical surface area, and that would help in increasing the capacitance. Okay, so that is, these kinds of strategies are envisaged in supercapacitors. Even otherwise, the electrochemical double layer capacitance is more than what you see in, let's say, inorganic capacitors, okay, so which do not involve electrochemical double layer. Okay, so we will address these issues more when we look at capacitors in the second half of the course. And then here, what we try to emphasize were three kinds of behavior. These are, or two kinds of idealized behavior and what is typical behavior. Two kinds of idealized behavior is the totally depolarized electrode and totally polarized electrode. A question that was raised was that when you are in this region, where is the energy being stored? So first, let's understand what is being plotted. Here we are plotting in both the graphs. We are on the x-axis, we are plotting the electrode potential. Okay, on the y-axis, we are plotting the current that is transferred across the electrode-electrolyte interface. So the direction of current is different in this regime, and it is opposite to the current in this regime. Okay, so we typically say this is the electrode is polarized in the anodic direction in this regime, and it is polarized in the cathodic direction in this regime because of the direction of current also changes. So when you ask the question, where is the energy? Where does the energy go when you are in this regime? That is, there is no Faraday current. What do you mean by Faraday current? There is no electron transfer. Okay, so that's whenever you refer to a Faraday current, we are talking to a current that is because of electron transfer across the electrode-electrolyte interface. In this region, there is no Faraday current and there is no non-Faraday current also. Okay, so non-Faraday current is because of it's a capacitive current, right? So Q is equal to CV. Okay, so if you look at this relationship, Q is equal to CV. So dQ by dt, which is current, can also be because of C times dE by dt. Okay, in important experimental technique called cyclic voltammetry, we would see this kind of capacitive current. That is, you would be in that experiment, you typically vary the electrode potential with time. Okay, so there is a finite d phi by dt. Okay, even when there is no Faraday current, because of a finite d phi by dt, you can have a capacitive current. So dq by dt in that case is C times d phi by dt. All right. So that's called a capacitive current or a non-Faraday current. So in this here, we neither have a non-Faraday current nor have a Faraday current in this regime. So when the electrode is polarized, there is charge polarization across this electrode-electrolyte interface. What do we mean by that? So when we are in this regime, so as we change the electrode potential, we are in effect changing the amount of charges that are stored on the electrode. In response to variation in the charge that is present in the electrode, more there is, in response to variation here, there can be variation on the structure of the electrolyte, structure of the interface that is present here. Okay, so there, if you add more negative charges onto the electrode, more positive ions can get bound to the electrode interface, or there can be more greater polarization of the dipoles that are present in this region. Okay, so the nature of the electrode electrolyte interface changes, okay, in such a way there is more charge polarization, but still there is no current that is present in this region. Okay, there is no electron transfer that occurs between the electrode and electrolyte in this regime. The electron transfer starts only after this point, and after this point, in the cathodic region, in the anodic region, after this point. Okay, so that's what was being conveyed from these schematics, and also the definition of overpotential. Okay. Lastly, we also conveyed that there can be three kinds of overpotential. Okay, there is a overpotential, what is called as a ohmic overpotential. The response of, there are three different responses. Based on three different responses, we attribute three kinds of processes that are occurring. Okay, so here again we are talking about an overpotential that is relevant to the electrolyte. We are not talking about the electronic conductor here. We are only referring to overpotential that is present in the electrolyte. Okay, so the typical response for this behavior is that the current varies linearly with ohmic overpotential. If such a behavior is observed, we'll see. If it is observed, we will call that this behavior as ohmic overpotential, the response due to an ohmic overpotential. Okay, so we will look at these things in greater detail. Okay, we are just introducing these topics in this lecture or in the previous lecture. And there is another behavior which is observed here, right? So when the overpotential increases, that is overpotential, mind you, it is defined in this manner. When you want to increase the overpotential, you have to increase the electrode potential. Okay, that is, or change the electrode potential. That is the only way you can change the overpotential. When you change the overpotential, let's say when you increase the overpotential, despite the increase in electrode potential, the current does not change. Okay, the current is saturates. Current is saturated. Okay, it is saturated here. It plateaus off. It can plateau off here also. Such a behavior is attributed to a different kind of physical process, physicochemical process. We will address this at a later stage. Okay, right now we are just documenting that there can be three kinds of behavior. Okay, this is called the ohmic overpotential. This is called overpotential associated with transport of ions to the electrode surface. Okay, that becomes limiting. The diffusion or the mass transfer of ions to the electrode surface becomes limiting. Because of it, there is a saturation of current. But what we will be seeing in the next lecture is what is called the kinetic overpotential. This is associated with electrode kinetics. There is an electron transfer reaction that is occurring. That electron transfer can be exponentially increased when the electrode potential is changed. Okay, as the electrode potential is changed in this direction, the kinetic overpotential also increases. In response to change in the overpotential, there is an exponential increase in the current. Okay, so that is associated with electrochemical reactions. Okay, so there are three different reasons why you see these three different current response to overpotentials. Okay, so we would address this response in the next lecture. Thank you.